Hey everybody, my name's Phil, and in this video, I want to demonstrate one possible approach to reverse engineering encryption algorithms from binaries. Now, to make things interesting and to make sure I don't get in trouble for violating anybody's intellectual property, I'm going to be using as my example a malware executable, which was installed on one of my servers by a hacker. These same methods that I used for reverse engineering this executable can also be used against many other types of software. The first step in pretty much any attempt at reverse engineering is going to be disassembling the binary. Since this is a Linux ELF binary, I can use object dump to disassemble the executable. Once we have the disassembled binary, we can look through the functions included in the binary. The function I'm going to focus on is called encrypt_code. I noticed this function is called in many places throughout the executable, including in the exec_packet function and the decrypt_remote string function, and both of those sound interesting, so encrypt code seems like a good place to start. If we look at the disassembly for this function, we can see that it doesn't make any calls to any other functions. This is good for us. It'll make our work a lot easier, and it also implies that it's very poor encryption. Now, if you're good at reading assembly language, you can figure everything out just by looking at the disassembly, but I'll save that for another video. In this video, I want to show how we can execute a kind of chosen plaintext attack against this algorithm to get samples of encrypted data which we can analyze to figure the algorithm out. To do this, I'm actually going to execute the executable on my computer. However, since this is malware we're dealing with, running it could be dangerous. So before I do anything, I'm going to cripple it so that it won't be able to do any damage to my computer. To do this, I'm going to look at the disassembly, find the main function, and then open up the executable in a hex editor. Find the main function in the hex editor and replace it with a series of hexadecimal 9 zeros. The reason I use 90 is because 90 is the opcode for no op on x86. And at the end, I'm going to put a C3, which is the opcode for return. Once the main function has been destroyed, I can safely run the executable and it'll just exit without doing anything. Note that this works in my example, but it is possible to craft an executable where the damage is done either before main is called or after it returns, so you should check to make sure this isn't the case if you're working with malware. What we want to do is replace what was in main with our own code so that we can call encrypt_code, pass the data we want to it, and print out the result so we can analyze it. We could use C to write the replacement code, but it will be much easier to do in assembly language. We need to figure out what arguments the function needs. You might get this via educated guesses and trial and error, or you can check if debugging symbols are included, which is very common, but in this case there aren't any. Besides having debugging symbols, the easiest way is to just read the disassembly. Look for anything being popped off the stack in the beginning of the function. Often, compilers use move instructions instead of pop instructions to do this, but they're usually easy to identify. Notice the moves referencing the EBP register with small offsets? Looks like this function has two arguments, and the second one looks like it's an integer, so that's probably the length of the data, leaving the first argument to be the address of the data. We also need to remember, when writing the replacement code, we can only call functions that are already included in the binary, and we have to call them by the memory address where they will be loaded. We can easily find this information by looking at the disassembly. Any data we use also needs to be in memory somewhere. Since the function has no output buffer argument, it looks like it encrypts in place. This means the data we use needs to have read and write permissions. We could allocate memory by calling brk or mmaps as calls, or we could just use a memory address from the data section of the binary. I used object_dump to locate a series of 64 null bytes in the data section. We could replace this with any input we wanted, but all zeros is probably the best input to start with. Now we can enter these memory addresses into our replacement code for our call to the encrypt_code function and for the data we want to pass into the function. I suggested using assembly language for this code instead of C because it's much easier in assembly language to call a function by its absolute address, and also because the resultant binary native code will probably be much shorter. Remember that the replacement code needs to be shorter than the original main function. Assemble or compile your replacement code, then run that through a disassembler. Locate your replacement function in the disassembly. Now copy the binary data of your replacement code, using a hex editor, into the target program, replacing your no-ops in the main function. Now to be safe, disassemble it again, and check to make sure that it all looks like it should. Now finally we can run the edited target executable and save the output. The output should be the sample we were looking for. Edit the executable a few more times and change the input data. I find that all zeros is a good place to start, then all bits set, then just try changing one byte of the input at a time. There's a lot you can learn by looking at and comparing the results of the algorithm, and when you think you figured it out and can recreate the algorithm, you can compare the results of your algorithm to the original and verify that it's the same. As for analyzing the output, there are several things to look for. Is every byte of the result the same? Is each byte affected by the previous or next byte? Does the output repeat? Notice, in this case, the output does repeat every 16 bytes. That's because this algorithm uses a 16-byte long key. That's all the time I have for this video, although there's still a lot more to talk about, so there should be more videos on the way. Subscribe if you don't want to miss them.